So maybe let me reintroduce myself. So I'm
No, fine.
no.
Go ahead.
Okay, so this is an astrostatistics project for estimating the luminosity functions with the presence of dark sources for a population of X-ray sources. And I will also introduce a new statistical method that I've been developing for this project.
Why is dark in quote? Is that not really dark, or you just don't know?
Well, we don't know whether or not they are really dark, but as far as we can see that there's no signal that we receive from them.
So this is it related to dark energy? Any of this?
No.
Just because you don't know what it
They're
is.
truly dark. We can't see them.
But you know they exist.
Yes, we know they exist. Yes.
Imagine you have a population of light bulbs.
Yes.
Some are dead and some are alive.
Yeah.
So you light them all up, and then you want to know, well, I think something like this, with a distribution of those that light up. You know how many, you want to know what that distribution looks like. But some of them, are just too faint, and below your limit. Some are just dead.
If I may extend that analogy a little bit,
Yeah.
it's like having the light bulbs connected to solar panels. Each light bulb to a different solar panel, and some of the solar panels are under clouds
I see.
or at night.
Okay. But you guys know existed.
We know that it
That's
exists.
that's not an assumption. That's
We're
good though.
We'll find out more about that.
Okay.
Yeah.
All right. Okay. I like the connected with the solar. That's a good one.
Okay, so I think this picture actually demonstrates that light bulb example as well. That for instance, in this picture, the yellow circles represent the X-ray sources that we have detected in the X-ray catalog, whereas the blue circles represent the sources that we detected in the optical catalog, that we know that they can potentially be X-ray sources, but we didn't detect any X-ray from them. And so the main.
Can you
sorry.
move that thing?
Oh,
off?
right. Okay. Sorry. I didn't realize this.
Oh, go to more and no. Go to more and say turn off. Hide floating meeting controls. There you go.
Okay. So the primary objective of this
You want to be dark.
Parts of this presentation will be dark. Yes.
the primary objective is to estimate the distribution of X-ray sources among a population to estimate the distribution of X-ray flux among a population of X-ray sources, but there are a few astrophysical challenges arising. The first is that there can, as you can see in this picture, there can be a very large number of X-ray sources in a population. And the second is that there's always the presence of the background contamination. So for example, in this picture, each white dot represents an X-ray detection. But as you can see, that there are lots of white dots outside of these optical or X-ray sources. So this picture shows that there can be lots of there can be lots of background contaminations that making it hard for us to distinguish the sources from the background. And the third astronomical problem is that as you can see in this picture, like lots of the X-ray sources can be dark. And the fourth problem is that there can be lots of overlaps between the regions where we detect the X-ray sources where we detect the X-ray photons for each source. The structure of this presentation is as follows. Next, we will introduce some key astrophysical concepts, and then we will tackle each of these astrophysical challenges one by one using some statistical solutions. Then at the last, we will introduce a new statistical methodology for marginalizing of some parameters in a model. So, too much. Okay. So there are a few key astrophysical concepts that we need to introduce here. So the first is the point spread function. So for each X-ray source, the point spread function gives the radius of a circle such that 90% of the X-ray photons from this source are expected to be detected inside this circle. And the next one is the source intensity for each X-ray source. That's the expected source count for each X-ray source. And the third one is the luminosity function that gives the distribution of the source intensity seen in an X-ray source population. And finally, as a remark, the inference for the source intensity parameters, lambda I here, are via the SI, which is the number of photons from each source by the formulation of our model. And let's look at the first astrophysical problem. Is that, well, as I said, there can be a very large number of X-ray sources, and these X-ray sources can have an independent, identically distributed, can be independent, identically distributed. So naturally, this gives us the structure of a Bayesian hierarchical model as this. So, at the beginning we have the mean and variance for the whole population of source intensity parameters, and then each source intensity parameters are independent with each other, and each one corresponds to one source photon from one source photon count from one source. And so this is the main structure for the source part of this model. And let me introduce some of the deterministic variables in this model that I'm not going to change during the inference process. So the first one is the area of each source region, and the second one is the exposure time that we look at the sources and the background. So the time that we look at the sources and the time that we look at the backgrounds are the same. Both are key here. And the third one is the proportion of photons from the source that we expect to fall inside the source region. The fourth is the telescopic effective area of the source at the source location, and also the area of the backgrounds that we look at. And finally, the location, we assume that the location of each source is known. So, and on the top, it's just it's just a demonstration of the structure of this model, and we are going to look at the details of this structure constructively in later slides. The next astrophysical problem is that there are non-homogeneous background contaminations in the source regions. And this is because the universe is three-dimensional, but we can only take two-dimensional, sorry.
The PSF and EI constants are related. I think that you call it the PSF, the point spread function.
Sorry?
The point spread function that you introduced. Is it related to the EI constant?
No, I think, well, as far as I know, that the EI constants are telescopic. Like they are things. They are the.
Can I?
Yeah, maybe you can explain.
So the PSF is a spatial thing. It tells you how broad a point source ends up looking like on an image. The EI is the sensitivity of the telescope. So it's effective. I mean, in a simple telescope, you have a big mirror, right? So that changes whatever. That gives you an area of the collecting area. But usually this area changes according to the wavelength of the photon. I mean, because the mirrors have different sensitivities, and when you include that sensitivity, the geometric area reduces. It's always smaller than the total geometric area of the telescope, and it's called the effective area. that's the EI. It changes,
Converts from photons to counts.
yeah,
Your detector measures counts, but those are related to the photon field, the flux of photons coming in per unit area. So you have to convert that.
So those counts are electrons that came off the.
They're photons. Like a count is a photon.
They'll be technically
event.
converted into electrons, and there's some readout electronics, but we don't do that. We assume that's all worked out already, and we know what a
It-
photon is.
you get a spike in the current, that's the detector registers. And that's one event, one count.
Yeah.
Many electrons, one count.
Okay.
Okay, so for the background contamination, this is because the universe is three-dimensional, but we can only take two-dimensional images of the universe. That's why there are always objects that's behind our objects of interest that can also emit X-ray photons, but we are not really interested in those X-ray photons. So the background contamination is almost everywhere, all the time. It's everywhere all the time, and that also the one issue is that the background contamination can be inhomogeneous, such that the contamination rate will differ depend on the projected angle in arcing. That's That's how high we look at the sky. So
Do you mean how far away from aim point, from the center of the image it is?
yes. So this motivates us to introduce some latent variables B. That's the number of background counts in each source region, and also this makes our primary source of interest, the SI, the signals from the source, not directly observable. So what we can observe is always a mixture of the signals from the source and the noise from the background. And so to have some more information on this background contamination rate, we observe some pure background areas. That gives us the X. That's the count. That's the X-ray photon counts in the pure background area. And
See, this third bullet point there,
Yeah.
and compared to that X given C, where you have that, I mean, you're assuming that, you're not assuming that the background contamination is inhomogeneous. I mean, you're actually assuming that it is homogeneous.
that's why. That's later on. That's
Okay,
that's in the
right.
later slide. Yeah. So I'm just introducing the structure here. So from some of the detections of the pure backgrounds, we get some information on the contamination rate parameter, and then we use a mixture of these contamination rate parameter and the source rate parameter to model what we observe in each source region. And the one previous solution to this background contamination problem is that we can simply use an average background rate at the region, and then use the observed number of photons in each source region to subtract this average background photon count. But however, sometimes the source is so faint that we only observe a few X-ray photons in that source region, but the background can be quite strong. So this will give us negative source counts. That's a negative count of photons. That's not physically possible, so it's not a very good statistical solution to this background contamination problem. And so here we use the more sophisticated model here that includes the background contamination rates in the observed counts directly. And So as Renee mentioned previously, that we consider a vector of background contamination rate, where each element in this vector corresponds to one background region, and then we observe the pure background counts in each one of these regions, and we assume that these sorry.
I'm wondering, in the setup, do you have like observations for like a single? Like you have a source, but you have multiple observations for, and so you have a kind of from different angles that you observe with different telescopes on Earth. So you have like different telescopes on Earth. You observe the same source, and so the background is different, right? Or is it not?
The sources are so far away, it doesn't matter where you
Oh,
look
okay,
from.
okay, okay.
It's, you'll always see them from the same side.
So you have like a single background associated to like a source.
In this case, these are all, we're only looking at like high energy data sets. So it's all,
It's all from space too.
there's no
Oh, okay,
ground
okay.
information.
But of course, there's different regions in space. The telescope flies around the Earth, right? It's not a constant position in space. But where the telescope is doesn't matter because it's tiny compared to.
So the capital A is effective area?
For the background.
So what is the capital A?
So capital A, yes, that's the area that we are measuring the pure background counts.
Oh, it's not the telescope, it's not the effective area, it is the physical area on the image.
So the C is like per area.
Intensity
measured.
per unit area.
And the T is the exposure time?
Is this.
What's a little a?
That's the area of the source region, of each source region.
The counts that you collect source.
You could go back to your first picture and illustrate that, Siyang.
Our first picture.
You see, those are the AIs or the little circles, right?
Yes. That's the little AIs are like, for example, the area of this yellow circle. That's about it. All the blue ones.
But for those ones dark, you don't know what the area is.
No, it's defined by the PSF, so we know exactly.
Oh, I see.
So it's.
You know where
it's
you're
not-
looking. You don't count any photons, but you know where you're looking.
You know what, okay.
I mean, we are making the assumption that everything in this image is a point source, which in this particular case, I happen to know it's NGC 2516, it's a star cluster. So we know it's true, but it's not always true.
So the capital A is much larger than this little a is.
Yes.
What is the E there?
E is the telescopic effective area.
Oh, that is the effective area.
E for effective.
Oh my God, we're so, because we used to use A as the effective.
Yeah.
We should have used E, because we said
Effective area.
We usually do
Effective area.
A,
E for
sub,
energy of
A sub F, UFF.
EFF.
because impossible, you're worse than mathematicians.
You know,
give us more characters.
I like that. That's a good one.
There will be more maths later in the second part of this.
Okay, so what's a little r? Sorry, I have so many questions. Little r is what?
Little r, that's the proportion of the photons from the source that are expected to fall inside this source region.
So that's 0.9 because you've defined your source region to
Yes.
capture 90%.
Yes.
It's an integral over the PSF.
I see.
Okay, so we also assume that the background is homogeneous within each stratified region. So that's how we can observe. That's how we can use the observation of a pure background to infer the background contamination rates in each background region, and then use the contamination rate in each background region plugging insights into the likelihood for each observed number of photon counts in each source region. And we also need to I also emphasize that the S and B are not directly observable. The background content, the number of background photons and the number of photons from the source in each source region are not directly observable. What we can observe is always a mixture of these two kinds of photons, and also the pure background photons. And so the background is just a latent variable in our model. And the next astrophysical problem is that there can be lots of X-ray sources that are dark, but we know that they are there. They are X-ray sources. For example, they can just emit so weak signal that it's just lost. That such signal is just lost in the background contamination, that we cannot distinguish its signal from the background contamination. That's one way that we lose them. The second way is that for example, if there are lots of, for example, if we observe lots of such kind of sources at the same time, like they overlap with each other, it's almost always that we can detect some X-ray photons. But if we only look at a single such X-ray source, it can be quite rare to detect that X-ray photons. Like, for example, if we just didn't observe it for long enough and we didn't wait until it to emit, that's also possible. And another possibility is that maybe some optical sources just don't emit X-rays at all. So
everything emits X-rays. Humans emit X-rays.
Okay.
Just very tiny little amounts.
So a question for you guys is when we say this is detect has a limitation because too faint you can help. So is that limitation of the current instrument, or it's like a mathematical lower bound you can never?
It's algorithmic.
It's instrument specific.
So as the instrument goes,
Gets better
oh,
and better.
gets better, is there any
You can see
physical limit the instrument will at some point can go beyond that?
Well,
No,
size
you can
of
always make a bit bigger mirror. Like
there is a
the size
limit.
of the moon or so, at some point you run out of material on Earth to make that mirror. But
Size of the universe.
Okay. All right, I got it.
Always the moon.
And also, what does detectability mean? Right? I mean, if you got a little source sitting on top of a galaxy,
Yeah.
you got an effectively elevated back diffuse emission, which counts as background. So it's harder to detect it then too.
So the statistical solution is simply to use zero inflated distributions for the population of distributions on the source intensity parameters. So for example, here is just a demonstration of a zero inflated gamma distribution, that there's a strictly positive probability for this random variable to be zero, and that this allows us to have some to retain the possibility that the source intensity parameter for example for this particular source region is just zero.
That's sort of saying that there's two populations.
Well,
One population, essentially, one population is zero, and the other population has some distribution.
but I guess there.
That is smooth and easy to compute.
I guess there is the possibility that we can't find a physical boundary to distinguish these two populations. Like maybe it's not quite natural to model them in two populations, but that might be a bit complicated.
This is a very contrasty figure. So because he's using a gamma distribution, it is possible that you can go all the way.
But
Most of the detectable part could be explainable as some sort of polygon.
yes, I just chose a gamma distribution such that the peak is quite far away from this zero component, but it's possible to have one that's very close.
But this seems like a really mixing two things, right? Because I would want to take your argument about two populations. If you think about, forget the instrument, right? There should be, the underlying there is a distribution of the intensity. So if you really think there's a lot of things cannot be observed, that density should be really peak around the zero, is it?
Okay, so
Whether
this is where it starts getting into real astrophysics. So
what?
for example, real astrophysics. Danger, yes.
Oh.
So for example, we know that stars evolve in certain ways by, the X-ray brightness of stars is related to how fast they're rotating. And how much they are rotating at any given time seems to go on two divergent paths. So it is perfectly possible for there to be truly two different populations of stars, one of which is X-ray bright, and the other one is X-ray dim and not detectable. I mean, maybe with a much bigger telescope, we would see both, and then we would see a camel, double bimodal distribution.
Yes, yes.
With most everything that we're seeing, we wouldn't see the dimmer population at all.
I mean, that seems to me like the modeling, just if just to what you said, is really a mixture of the two. One is dimmer, one's not dimmer. But if even for the other one is a truncated problem, right? Because let's say you don't have that, they always emit something, but your instrument. So it's basically, that's a truncation problem. You don't need to model. If you do the zero gamma, inflated zeros, that means you believe there's another population.
Yeah, I mean, there's, so what, if you can go back to the first image.
First, okay. I should really put
So
that everywhere.
So the yellow circles here are X-ray detections, and the blue circles are from an optical catalog of the same cluster.
I see.
So just look at the number of difference, the difference there between how many are detected and how many are not. So there's clearly a very large population that is not detected. And again, it is possible that it's just a power law that keeps going up until everything is detected. But there's a possibility that there isn't.
But would you be interested in, because the way you're modeling is, will you be lumping these things together? Whether something is really.
So that's why we're using the zero inflated gamma.
No, zero inflated gamma, you will still lump the two things together, right? Because you still have this, cannot be detected by instrument.
Yeah.
Or does not emit.
Yeah.
These two things are together,
Sure.
right?
Yes. Yeah.
No,
Would it
those
be
are,
better to, go ahead.
both of those things exist. And they could end up in either of those two distributions, right? You could have undetected X-ray sources.
Yeah,
But that doesn't mean there's not photons. They're just not detected.
Correct.
They're not distinguishable from background.
correct.
And those sources could end up, with a certain probability of being in the zero delta function, and a certain probability being a low value in the
Yes,
continuous
yes.
distribution.
Yes, that's what I'm getting at. But does your model currently, can you go back to the model part, capture that? I saw the model does not capture the second part. The gamma,
They're both there.
no, because this model does not really, what I'm saying is that if it's a truncated gamma problem. Let's say you don't have the zero inflated ones. Just observe the truncated part was long enough, you can estimate how much thing being truncated. Right, because I have these parameters, it's estimable from the tail. So you can, according to the curve, you're gonna go just about how much is being truncated.
It's not really a truncation problem. It's just that there's undetected sources.
But
I
that's
mean,
truncation.
ultimately, what you want to do is see if that zero inflation is better than the gamma distribution by itself. So that would be, is there evidence of really essentially dark sources?
Well,
I mean, you have this truncation problem
Yeah.
because there is a detection. What he's proposing to do is bypass the detection. So there's not going to be any detection, only estimation.
Just
No,
looking
no,
at raw photons, not worrying about whether or not Vinay was able to detect the sources or not.
They're only raw counts everywhere.
You're basically going to test whether or not this pi sub d is equal to 0?
Yes, well, we can just get a result of that from the posterior sample of the pi-d. So,
but we know the pi d is not gonna be zero. You guys just said there are those things.
But that's a hypothesis. I mean, he's got a physical model, he's not sure it's right.
He can test whether the pi d, how strong pi d should be.
Right, okay, I see. I still follow your point. I was trying to do a little bit more refined, saying if you believe the gamma models, you can actually you can see whatever. So how much is because instrument and how much is beyond that is not.
Yeah, the problem with that again is this is what Max is working on, right? The log and log S problem. So you can you can assume there's a power law distribution of intensities and account for incompleteness and push it all the way back.
Mm-hmm.
So this is just change, instead of using a power law, using a gamma.
Yeah, eventually I'm just going to replace the gamma by power law as well, but I'm just not up to there yet. So
So in this equation, it seems like you're defining dark sources, those which have zero flux, which is an oxymoron, isn't it? Like, these things are not emitting at all, and you're hypothesizing.
Doesn't that make it a tautology, not an oxymoron?
Well, one of those.
No, it's a
That's
model,
a
it's a model, right?
Yeah.
So if you want to know if.
So
if
is this conditional on being detected in the optical?
There
Or
is-
not?
No.
Yes, it's
Only the
conditional.
optical.
Oh, so conditioning on is detected in the optical.
Yes.
This, okay, that's the part that I was missing.
Yeah.
You're defining dark source in X-ray as that is having zero intensity in X-ray, conditional on having it detected.
Yeah.
So we know that it exists based
We know
on
that.
another data set.
Yes,
And we're saying in the X-ray data set, we don't detect.
exactly.
No, you're saying that there's no emission in the X-rays.
There's no detectable emission, yeah, but yes.
No, this
Well-
is saying, this
Right.
equation says,
In this model.
We're getting rid of the detectable, right?
okay, I got it. Yeah, there's a conditioning there.
okay,
Yes.
yes,
There always is.
yes. Okay, so that's for the zero inflation part, like that's for the dark source part. And the next one, the next astrophysical problem is that there can be lots of overlaps between the source regions. So not only there's the background contamination, the sample of observations contaminate each other, because, for example, here we can only observe the number of X-ray photons in each segment of these overlapped regions. And these observed number of photons in each segment are not independent with each other. So that imposes some new statistical challenges for us, but it's we can simply reparameterize the likelihood. So, for example, now we consider the area of each segment, the effective area of each segment, and the proportion of photons, expected proportion of photons landing in each segment rather than in the entire source region. So now all the geometric things in the model are in terms of the segments rather than the source region. And now we can construct the likelihood such that the observed number of photons in each segment is just a mixture of the photons from all the relevant sources of that segment, and plus with a mixture of the background. And so we just update our likelihoods in such a way.
So let me,
Yeah.
I want to correct the terminology you keep using. These are not mixtures, these are just a sum.
Okay.
Mixture means summing of the densities,
Okay,
not the
yeah,
random variable. This is just a
Okay.
sum, it's not mixture.
Yeah, I was meaning to say that a mixture
Yeah,
of photons.
it's right, but it's just, you got, when
Okay.
it's considered here mixture, this doesn't make mixture model. It's a
Okay.
different animal.
Okay. Yeah. Thanks. So this gives us a statistical solution to the issue of overlapping source regions. And so to summarize, the key features in our statistical model is that this is like for the signal part, this is a Bayesian hierarchical model. And we have background contamination, a vector of background contamination parameters, and we have a population of zero inflated distributions for the source intensity parameters, and also we have modified our likelihood so that we can we consider the overlaps in the source regions. And here is a Bayesian deck that summarizes the model. That first we start with the population mean and population variance for the population of source intensity parameters, and then we also need to consider the proportion of dark sources, and then we transform these parameters into these source intensity parameters into segment intensity parameters. It's just a mathematical transform. Sorry, I forgot to mention this part. This is the this part. It's just a mathematical transform, and this part on the top, and then we also consider the background components, the background intensities that generates the background counts that that's contaminating our source counts and also the pure background counts in the pure background regions. And then these background counts and source counts together they give us the observed counts per segment.
Sorry, what was exactly the pure background?
Pure background is just a region that's outside of our population of source of interest, and we measure the X-ray counts in that region.
The region where we know there's no stars.
Okay.
Which does not in reality mean that there
Sure,
are no
but
stars.
the region that we know there are no stars.
But how does it help you with like the background that's related to the actual region of space where you want to observe the source?
Yeah, I mean, effectively the gaps, again, but going back to the image one, the gaps between where there are no circles,
Yeah, for example here,
whether no yellow, no blue.
but you can still observe some X-ray here, like these white
Photons,
dots.
you always
Yeah.
see photons.
Then you have to rely on uniformity of the background.
Yeah, that's what we started with, but I believe
But-
he has figured out how to do.
Yes, but we stratify the background such that depending on the projected angle, such that where is it? Maybe it's here. Yes, we stratify the background such that we assume that the background is homogeneous within each stratified group.
Oh, he's done it in annular rings.
And
Oh,
this
okay,
rest-
so you have a model essentially, it's empirical, but you have a model for the uniformity of the background.
Yes. And with this model, we just do a simulation study, a very simple one. For the start, we assume that there's no overlaps between the source regions, and we assume that for now the background is homogeneous. And so we simulate some data according to the characteristics of NJC 2516, the Southern Beehive cluster, such that we simulate the data with the exposure time, the area of the background, and the background contamination rate being set according to this cluster. Be set to one observation of this cluster. And also to make the computation easier, we reduce the size of this cluster such that we assume for now there's only 10 sources in this cluster. And so this makes the dimension of the parameter space 14 because there's 10 source intensity parameters plus 3 parameters for the zero inflated gamma distribution plus 1 background contamination parameter. And we assume these are the true values, which are just sensible values that are picked for these 4 parameters. And I follow these steps to simulate the data. That we first simulate some pure background counts, and then simulate the population of source intensity parameters, and then use these simulated source intensity parameters to simulate simulate the source counts, and also use the background intensity to simulate the background, and then plus them adding them together. That gives the source counts in each source region.
Wait, sorry, I'm confused a little. You say that the cluster size is n equals 10, meaning there are n sources.
Yeah, 10 sources. Yes.
So how can you have 14 parameters that you can fit with it?
Well, then, because it's Bayesian in terms of Bayesian, we first fit the 10. We first fit the 10 source intensity parameters, and then use the results of this. It's kind of using the results of fitting these 10 source intensity parameters to fit the other 4.
Well, no, I think he's asking how you can fit 14 parameters with 10 numbers. And the answer is it's a hierarchical model where you integrate out 10 of the parameters.
Bayesian can do anything without data.
Where
Yeah.
Okay, so we run this model on the on nested sampling with the package Dynasty, and here's the results. They all look sensible. That the true values in the trace plots, the the iterations converge to the true values, and here are the results of this results of the posterior samples. So, which is just basically sensible posterior samples. But
So these are posterior, these are the
sorry.
contour, right?
Yes, contour and density plots for
Okay.
the 4 parameters apart from the 10 source intensity parameters.
And so these contours, they don't look too normal, but that you have a theoretical expression for these contours as well.
Yes,
Okay.
well, or at least proportion to these contours. So,
Is it possible?
Well, you have to marginalize out the lambdas and then you would.
yeah.
Right, I was just wondering, is there any one of them you can do a theoretical numerical contour to just double check everything works?
Well, we can do that. Yes, there are ways, and that's by marginalizing out the lambdas.
Yeah.
And
Have you done that, CJ?
no.
Okay,
No.
I thought you had.
That might be worth doing it, just a reminder.
Absolutely.
Maybe you may remember that what you did,
Yeah.
with that contour real comparison, and we see problems there.
Okay. Yes.
That's years ago.
Sure. Yeah. So and actually the motivation for us to marginalize out the population of source intensity parameters is that there can, like for example, in larger populations, there can be a very high dimensional parameter space. So if we can somehow integrate out these source intensity parameters, then this is going to give us a parameter space of dimension only of only 4 dimensions, and that will improve the efficiency of the sampler and improve its, for example, for nested sampling, it will improve its convergence to the true values. But on the other hand, there's going to be no information on each source intensity parameter available directly. So if we would like to know something about each individual source intensity parameter, we will have to do a second sampler. That's exactly what Siyang Li has mentioned in the last session, that we know the characteristics of the whole population, but we don't have the information of each individual in this population now. So for this models having the source intensity parameters marginalized out, and so somehow I managed to do that integral, but I will leave that to the second part of the presentation. So I just run another nested sampling using dynasty again, and here are the results. As you can see, that these trees plots they converge faster than the previous trees plots. I will just quickly go back to this ones. So the convergence is much faster, and the iterations and the time for the nested sampling to run is also much shorter with the same stopping threshold. And now this, of course, this nested sampler is only on the 4 parameters apart from the source intensity parameters. And here are again the contour and density plots for the 4 parameters, again apart from the source intensity parameters. And because that integral here is a mixture of gamma and Poisson distributions, so here we call it the negative binomial parameterization, whereas previously we called it Poisson parameterization in the previous density and contour plot. And these two density and contour plots.
Why negative binomial?
Because here we are integrating out this likelihood here is Poisson, and this prior here, or like this distribution here is a gamma distribution. So it's kind of mixing them together, and that gives, by some statistical results, that gives the negative binomial distributions.
Negative binomial is the mixing the Poisson, the rating with the gamma, that can be negative binomial.
I was confused because I thought it meant mixing Poisson with Gaussian, but
No.
With gamma, it gives you.
These plots remind me of oysters. You should call them oyster plot. There's lots of oysters there.
Okay, so and these two, this plot and the previous density and contour plots are under the same scale. So as we can see, that they roughly give us the same story. That they have the similar shapes. And then let's
Yeah,
look at.
just 1 second
sorry.
on this. I think it's interesting that there are these sort of tails to low values.
Do you mean which parameter do you mean?
All of them.
Well, let's pick the one in the middle.
First
The theta. You
Yeah.
see that is, what is it? Is that the best estimate and, or the true value and the peak of the distribution are offset, but then you have a very skew distribution that has this long tail. Is that just because the weakness of how faint the sources are, and there can be, like, it can be zero or something? I mean, do you know what causes that asymmetry?
No, it's hard to investigate, to be honest, and plus this phenomenon is a bit consistent across the samplers. Like
Well, you can say that you're not there. The data set is quite small, and so you're not expecting the central limit theorem to be kicking in yet.
Be interesting to see that there's like a couple more sources, right? If you have 10 sources on average, 5 of which are dark because your
Yes.
pi is 0.5.
Yes.
There's only 5 sources that actually measure anything, so.
Yeah.
But-
That might be part of it.
But what's
Right, so-
interesting to me, without knowing any details, it because when your central limit theorem doesn't kick in, it could go any directions, right? But
Yes.
they're all positioned on this kind of smaller.
Yes.
Why that?
Yes. We haven't I haven't investigated that, and actually this phenomenon is more obvious in the result of the more complicated simulations that I am getting on.
Okay.
So
That looks nasty.
yes.
That's a nasty oyster.
So this simulation study.
Out of season oyster.
Yeah.
Sea cucumber.
Sea cucumber.
So this simulation study is now we consider the overlapping source regions and the inhomogeneous background regions, and we just simulate the data using similar steps, except now we use some real estimates of the pure background count, and we simulate the data using such a very simple geometric structure here, that we assume that the first cluster of the source regions belong to the first background region, and the second one belongs to the second, the third one belongs to the third. So, and this is the convergence. This is the trace plots for the nested sampling, but this time, as you can see, the convergence is worse. than
In this more complicated thing, do you still have 10 sources?
We have 8 sources, but 15 source regions in total.
8 sources.
No, 8 yet. 1, 2, 3, 4, 5, 6.
Oh,
CJ, maybe you could tell them why you have so few sources.
Because it's quite complicated.
It's hard.
Yes.
Yeah.
Yes. So.
And the whole point of your next section is
to marginalize out the source intensity parameters to reduce the dimension of the parameter space.
and if you don't skip some things, you won't get to what?
Sorry.
He says you need to be faster and stop
If you want to get to
answering
that
our
stuff, you need to decide what you're going to skip.
Yes.
Okay. So and so the convergence is much worse. As you can see, the oyster is much worse now, and it's quite interesting to see that the inference on the mean of the population of the source intensity parameters is the estimation for such is much worse than previous, and plus these phenomena, on the tail phenomena, are much more obvious than previously. And so the conclusion is that we have built a sophisticated statistical model for some hard astrophysical questions, and that it is possible to implement nested sampling for this statistical model, but the parameter space can increase a lot when we deal with the a population with lots of sources or with a much more complicated overlapping structure, and this will result in having the sampler suffer from the high-dimensional parameter spaces. So now let's look at the statistics aspect of the marginalization. So for now, for the rest of this presentation, the C now denotes the hyperparameter, and theta denotes the parameter, and Y denotes the observations in a hierarchical model. We are talking about this marginalization method for general Bayesian models, not limited to the previous astronomical model. And and I will walk you through the mathematical details in this marginalization theorem. So first, we have this Bayes formula for the hierarchical models in general, and we also have this law of total probability. So if we combine them together, like plugging in this into this, we'll get the marginalized Bayes formula, and we call this integral the model marginalization integral for the remaining part of this presentation. And we are primarily interested in computing or like finding this integral analytically.
So let me say this. I think that you might run into trouble to call this a marginalized Bayes formula when you submit a paper, because it's just Bayes formula.
Okay,
right?
yes.
You don't need actually any derivation, because you have a joint casino y, that's just Bayes formula.
Yes. Yes.
There's all the middle step you're going to get it. You don't need to derive those things, because that is, except for statisticians, it's not going to be anything new.
Yes.
How to compute that thing is a different story. But
Yes.
I think it's just saying you essentially have three variables, right? Casino theta y.
Yes.
You're just applying the
Bayes formula to some of them.
to
Yes.
some of them. So I think we
Bayes
just call
formula.
it Bayes formula.
Another Bayes formula.
because you don't want to raise just
Yes.
right. But now how to compute that thing? That's take time.
It's not only computing it, it's deriving it analytically under with
Sure.
some conditions.
Right.
So and
But
because
that just apply the Bayes
yes,
probability calculation. Yeah.
sure. So and because this is the parameter space can be high dimensional, this integral is high dimensional, so it can be quite complicated. So this method will rely on three highly non-trivial, complicated mathematical facts. You have to believe me on these three facts, and here they are. So the first one is the PMF of a Poisson distribution. The second one is the derivative of an exponential function, and the third one is the definition for moment generating functions.
Yeah.
I think everyone can agree with me on these three facts in this room. Here's the derivation for this based on these three very simple facts. So first we just write down the integral that we would like to find analytically, and then we realize that this is an expectation with respect to the prior distribution, like for the likelihood function. So and because we assume that we now restrict our attention to Poisson likelihoods, so this likelihood takes a certain form, and we can take out the constant take the constant outside of the expectation, and also so we can just simply realize that this minus here can simply be a -1. So we just rename the negative here as t, and then we realize that this is the derivative for the exponential, and like a high order derivative, and because this derivative is with respect to t, but this expectation is with respect to theta, we can exchange the order of derivative and the expectation or integral, and that will give us a derivative of the expectation of an exponential, and this expectation of exponential simply gives us the moment generating function of the prior distribution. So suppose if the moment generating function for the prior distribution exists at t equals to -1, and if we only have one parameter in the model and only one observation for this model, then this will give us a way to derive, to find the model marginalization integral analytically.
This is very neat. So you're utilizing the special feature of the Poisson.
Yes, exactly.
So you basically, and anytime you can, this is very neat. Every time you can convert the integration into derivative, you have a win situation. But of course, there's a hidden part. So this works for any conditional density theta given C, if there's a moment generated function existed, and if you know what the moment generated function is.
Yes.
Right. I think then by the same token, let me see, you're using moment generated function. Now I'm just thinking if there's a one for the characteristic function, but that's different because you're directly using this e to the, hold on a sec, because you do theta. So you turn that. Now that's interesting is this is very neat. So it's interesting that the larger the y, the harder it is to do it. You have to do more derivative. So small const in this case is actually beautiful.
But actually, because, well, suppose the moment generating function is simple enough, then the derivative will usually be simple enough, and then it will just be a linear recursion as a transformation for this moment generating function.
Yeah, no, that's great. Let me think. So is there anything other than Poisson, would this also work for other things? Okay.
That's later.
That's later. All right, okay. Nice.
Yes.
I like it.
Thanks. And so we can summarize it or like generalize the previous results into a multivariate case where we can have like in a Bayesian hierarchical model, we can have a population of independent parameters and one observation corresponding to each parameter, and then this theorem is going to give us the how we can derive the analytical form of the model marginalization integral using moment generating function. And this is the theorem that we used to derive the model marginalization, like how we do the marginalization of the source intensity parameters in our previous astrophysical example. And like without like for the simple simulation study without any overlaps. So here, because without the zero inflation part, the gamma Poisson mixture is just a negative binomial distribution. So we have easily verified that this theorem holds using the corresponding negative binomial densities. But if we consider the zero inflation part, which for the moment generating function is very easy to deal with, because by using the linearity of expectations, and also if we consider the overlaps, which is essentially a transformation, like a mathematical transformation on the source intensity parameters, that's also very easy to derive using moment generating functions. That's also easy to derive the corresponding moment generating function, which is like this. Like we can basically just plug in the transformations to corresponding parts of the moment generating function. Then we can derive a more generalized version of that theorem on a transformed and scaled population of the independent parameters. And this is what we can use for marginalizing out the population of source intensity parameters with the overlaps, like for the more complicated simulation study. And but however, there's no easy check this time because now essentially we are looking at the moment generating function for the transformed source intensity parameters, which has some very complicated and unknown distribution. It's very hard to derive the distribution for the population of segment intensity parameters. So So here we go. There's the first example, like even the simulation study example that shows that this whole theorem works, because that's the first simulation study. The simple simulation study is actually just using this theorem, so it's verified.
So,
using the code.
let's say n is very large, it does not really matter, right? Because once you have a closed form, and if your derivatives can be written in closed form, let's do a simple calculation.
Yeah, well, as long as we can find a derivative, then I don't think we can find this high order derivative, then I don't think there will be a problem.
Yeah, no, that's not a problem, but no, I'm just saying, there'll be a problem where,
Finding the derivative.
well, you can always do numerical derivative, but that's
Yeah.
gonna be troublesome.
Right, well,
Yeah.
didn't you run into trouble with the background case? Because of combinatorial derivatives?
Well, yes, because because there's the background contamination in our previous astrophysical example, then we had to do a multivariate convolution of the high order for this, and that can be quite troublesome.
But you could, just to be clear though, you could still write down a formula like this, but the nature of the derivatives were combinatorically many. Is that right?
Well, well, no, actually, I made some mistakes deriving the derivatives previous for my previous derivation. But so it's very easy to make the mistakes. But I think it is possible to find at least some general patterns when differentiating the moment generating functions, even though it's of high order. So essentially, we should be able to write it in terms of linear recursion as the as a transformation on the moment generating function. Although actually I made some mistakes I haven't reported to you.
So, this is, well, don't tell David, so you can correct me. But seriously, this really got me thinking, because there's something really curious about, I'm started thinking about, mathematics is never just by coincidence. This mathematical formula is telling us something. But I never have seen the data become an order derivative. That itself is very interesting. I was just thinking what that means. That's a very weird thing.
And actually, there's in the very last slide, I tried to interpret this statistically, but
Oh, good, go ahead,
Okay,
go
yeah.
ahead. We will stop interrupting you.
okay, it's fine.
No, you won't.
Thank you. Thank you. You know me too well, Dan.
Okay, so and these results can also be generalized to for calculations for the marginal likelihoods, because here we are just marginalizing out the population of parameters, and each parameter corresponding to one observation. But on the other hand, the calculation for marginal likelihoods have a very similar structure, where we just integrate out a single, like for the either case, a single parameter here, and one parameter corresponds to lots of observations. And that model marginalization integral becomes, so it's very true to see that becomes the denominator here in the at the bottom for the Bayesian formula. And so we can derive very similar results for the calculation of marginal likelihoods on the Poisson likelihoods. It's just this, and well, we can compare the previous formula and this formula and see that previously it was t equals to -1, but now it's t equals to -n. It's quite elegantly corresponding to each other. And also the derivative is just of the order of a sum of all the observations. And we can generalize this result for gamma likelihoods. So actually, I should have written out how elegantly they correspond to each other. But in essence, it still follows the same steps that but maybe I can just write the steps on the board later. But as a result, we can find the model marginalization integrals for gamma likelihoods in such a way that's using where this arrow here is just the moment generating function, but transformed on some scales, and then the m is the Milling transform, not sure if you
Yeah.
use that, but and this is the a derivative, but because the alpha, the shape parameter in gamma distributions can be fractional, so here we had to use a fractional derivative, and that's why there's a milling transform, and this here this denotes an integer like that's very close to the alpha parameter, the shape parameter, and because the use of because the fractional integrals may not commute, like the order of the fractional integrals may not commute, so that's why the assumptions here for this result to hold is slightly more strict for the Poisson likelihood, that now we had to assume that the population of this parameters, not this one, the population of the theta parameters is independent with each other. So
You may know I wrote an article on all these fractional derivative for the moments calculation.
not yet.
Yeah, so I will show you. But these fractional derivative actually, the calculation involves integral.
Yes, yes.
So in that sense, it's not really much a saving, because
But that's the milling transform. That's what milling transform here is for.
so as long as the milling transform itself, so if that's durable,
Yes.
right? 'Cause so there's a, there's still, that's harder now.
Yeah,
It's-
it is harder.
It's not as easy as.
Yes.
as the other.
Yes, and well, better if it's Erlang distribution, which is like only takes the integer shape parameters than the gamma shape parameter, then it would be easy again. Yeah. So, and the last slide is that maybe we can have some Bayesian interpretation on these formulas,
Okay.
because we have this very famous formula for calculating moments of a distribution, and that's very similar to our the formulas in our theorems. That but the only difference is that the calculation for moments is plugging in a 0, but here we're just plugging in, for example, the marginal likelihood calculation formula is just plugging in negative n. So maybe this formula can be a special or limiting case of our formula. So such that we can probably interpret the moments of a distribution as if this distribution is used as a prior, and then there's a Poisson likelihood or Poisson process, and we only observe this Poisson process for a very short time. That's possible, but I haven't done some rigorous mathematical derivations on that yet. Or maybe we can do similar things using the gamma likelihood.
I see what you mean, okay. We definitely can talk about this. I think this is a very interesting. Can I interrupt you now?
Yes, that's the last
You already
slide.
did it.
That's the last slide.
Page
Yes.
41, you already did.
Yeah, I know. But, okay, so although these are special kind of two Poisson, but Poisson itself actually, lots of distribution can be approximated by Poisson. So I'm just started thinking about this, at least there will be a way to create some approximated margin likelihood. You can even use them, as proposals and other things. Because I think that this might be really, there's something very neat about a Poisson, right? Because you have
Yes.
the moment calculation. But there gotta be other, maybe,
Right.
this actually, you know what, this actually reminds me that if it's not Poisson, let's say if you have, these guys love the power law. If you have power law, actually can do similar things, but that's the Laplace transform then,
Yeah, maybe.
right? You don't use the moment general function, you use the other thing. So there's these, there is these transform things, so there might be more general thing can be done, yeah.
Yes, actually, when the code was being written for the simulation study, I was using Laplace transform, but then
Sure.
later on I realized that this method can probably be generalized using by writing it in terms of the moment general function. So yeah.
This will be actually really good news for astronomers, because you guys like Poisson. So now you just need to learn a little bit more moment general function. You can turn lots of integrations into derivatives, seriously.
Yeah.
Into derivatives. But there's something really quite interesting though. This is evaluated at minus n, right?
Yes.
But it's also the derivative itself. So here's what I'm getting at. If n is very, very large, you will have limiting behaviors for the moment general function itself.
Yes.
Right? But if your observation themselves is fixed, let's say n goes to, let's say you observe, right? That's like a sum. Like if the average of the y's is small, n goes to very large. This formula itself might provide you with a kind of approximation to that density itself. Right, because there could be some kind of a, small Poisson asymptotics. If you,
Small Poisson,
well, meaning the counts are low counts, not small Poisson.
yeah.
Low counts approximation, right?
Because of course,
once
the Poisson is an
derivative-
approximation to the low success rate binomial. When-
Yeah, this should, I'm just curious, but this, right, because, if let's say the count is small, low, then the sum of ys, let's say it's low, but n can be large, there gotta be some asymptotics there. Yeah, it's very.
That is the case we would encounter when we have a spectrum with a large number of empty bins.
Yeah, this might actually give you a very nice,
We should tell Yang about this,
yeah, it's interesting.
because how do you take the log of this thing?
How do you take a log of this thing?
Yeah,
No, you will first, well, actually,
Yeah.
that is actually a good question.
Actually, I'm trying to work on this as well, but it's not successful yet.
I was thinking about this because you're using moment-generated function, right?
Yes.
But if you use cumulants, then you operate on the log scale of the moment-generated function. And then hopefully you might be getting, that might be getting more flexible results.
Yes, I looked at some relevant literature actually just a few hours ago on, for example, if I can replace this moment generated function by cumulant
Yeah.
generated function, but I think there is actually one paper that's published last year, but it's not derivative on the cumulant generating function, but it's also something similar to this. I like to draw to your attention that's in this signal processing. I think that's the area. It's actually differentiating a conditional expectation that will give you the cumulant
I see.
when z equals to x plus y and x is an independent Gaussian from y. So that's a kind of similar result, but I think similar things can indeed be done for cumulant generating functions, except that we don't have the elegant derivation of the elegant derivation here, because the cumulant generating function itself is a log of an integral, but it's not just an integral directly. And secondly, maybe we can investigate the relationship between the high order derivative of the moment generating function and the high order derivative of the cumulant generating function, because I'm sure there can be some kind of relationships between them, and then do one where the other. So.
Yeah, this definitely has lots of things to explore.
Did you try any distributions besides Poisson and Gamma?
This is actually, well, I tried for normal, but for now at least it didn't success because
Which part is normal? You mean normal anything?
no, I mean normal likelihood.
Normal likelihood.
Yes, because this gamma is in the likelihood. That Poisson is also in the likelihood, and it's the prior gives the moment generating function, and then it's either Poisson or gamma likelihood.
So, but then you do the reversed approximation, right? Because Poisson for large lambda become a normal.
Oh, yes,
So
yes.
you do reversed approximation.
Yes.
Approximate normal by the Poisson.
Well,
And then you get very high order derivatives, right? Because as lambda gets big, you would expect
I
x
can
to.
have good, yeah, but you yes.
revenge.
but well, I think because I was the way that I was trying to do. Anyway, I can write, but
Yeah, chalk is
There's
There,
chalk
there,
in the
there,
middle.
over there.
So because I was trying to derive a result for natural exponential family in general,
Yeah.
and that's the exponential of the it's usually x, and then the parameters at the minus of plus a function of
I see. So
yeah.
you use the canonic parameter.
Yes. Because there are two terms in this kernel of this of the distributions in natural exponential family. So I either differentiate this part or I differentiate that part. Differentiating this part gives the sum. Differentiating that part gives the gamma. So that's the correspondence between these two results.
I see.
Yes.
I see. But nothing to stop you to do. You could try to get that, well, it's a bit harder. You could use a multivariate moment general function. The joint moment general function has two arguments. You can do the cross derivative, like a partial derivatives. Still works, right?
That's actually what I'm doing here. It's just a
Yeah, in this case, yes,
yeah.
right. That's in this case.
Yeah, that's the one. So it corresponds to transformed Poisson.
All right, so it's at 1:26-ish. So
Next we see is slide 43.
yeah, yes, let's look at
43. That's just a not too good to say. That's why I put it to the last. Or like it's just a
DAG.
yes DAG for the comprehensive DAG for the model.
what's the DAG?
The directed arrow.
Oh,
Acyclical. So can we just remind everyone that Siyang is here, or here, he is there for 2 more weeks? So
only 2 more? I thought it was mid-May.
Yes, mid-May until the
3 weeks.
17th of May. So.
okay, more than 3 more
I'll
weeks.
send you my paper and we can talk.
Oh, sure.
Yeah.
Thanks.
So, I'm glad to see fraction derivative. At one time I
That
worked
is
on
so
those.
bizarre.
No, fraction of it's actually stuff from Fisher. Fisher was using fraction derivative. So I wrote if you guys wanted to, I wrote a whole article about it. And there's also, you can use, you can do negative moments, right? Sometimes you do negative moments, the fractional moments, everything can learn from the moment general function. But except that the negative moments, it's almost like the mathematical workout is integration. And the fraction moments involve both derivative and the integration. Derivative takes care of the integer part, the non-integer part becomes the integration. It's very cool stuff. So there's all these, and I used them for some really hard problems. Essentially, it's all a form of Laplace transform, because Laplace transform is very powerful.
Yes.
All right. Okay,
Great stuff.
thank you, Siyang. That's nice.
So we still have 2 lunches here. Who want to claim to be the guest of James?
We can, somebody wants to make a
Should I just mute and stop?
Yeah, I think, are there any other questions from?
Is there any questions on the chat?
No, they may have just given us the
All right,
call
see you all next week.
Okay, bye-bye.
Bye.
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 Bye.